All right, now we're going to move past parabolas and quadratics, and we're going to get into higher degree polynomial functions. So the deal with a polynomial function is it can be written in a very specific format that looks like this in the most general sense. Now, there are a lot of symbols going on here. And in order to understand what any of this means, we say the variable x is going to show up in the powers counting from x to the n down to 1 less power, 2 less power, so on and so on, until we run out of powers of x and we have the constant at the end. And these a sub n minus 1, and so on, are the coefficients on each of those terms. It still seems like a lot to take in, so let's look at an example. F of x equals 3x to the fourth minus 5x cubed plus 17x squared minus x plus 10. Okay, so in this context, we're looking at x to the fourth power. So that n is 4, which means this 3 represents a sub 4 corresponding to the x to the fourth term. Then we count down 4, 3, 2, 1, and no powers of x. So this negative 5 is the coefficient a sub 3. The next number, 17, is a sub 2, corresponding to x squared. And then negative 1 here is a sub 1, and this 10 is a sub 0. Okay, now once we have this idea and we can understand what these symbols mean, we can discuss the most important features, at least most important to us right now. This n represents the biggest power of x that occurs in the polynomial, and this n is what we refer to as the degree of the polynomial. So in this polynomial function, 4 is the biggest power of x. So we say the degree of this polynomial is 4. The next thing we look at is this a sub n. So that's the coefficient on the biggest power of x. This is what we call the leading coefficient. Leading because when we write the polynomial in this format, it shows up first, and coefficient because it is a coefficient. So in this case, the leading coefficient is going to be the coefficient on the highest power of x, so that would be 3. Let's do another example just to lock it in. So if I have f of x is equal to, let's go with negative 1/2 x to the 17th plus 3x to the 14th minus 19, let's say. And I didn't put all the powers of x. When I look at the degree, I only look at the highest power of x that occurs, so that would be this right here. So I'm going to say the degree of this polynomial is 17. And the leading coefficient is going to be this negative 1/2. So the leading coefficient. And there we have it. Now, let's start a discussion that's eventually going to lead up to what we're going to call end behavior. So we'll start with an example function, f of x equals x cubed plus 2x squared plus 3x plus 4. We're going to make a table. We're going to say x and f of x. So we'll start with x equals 1. So I plug in 1 cubed is 1, then 2 times 1 squared, then 3 times 1, then just 4. Add them all up, I get 10. I'm going to jump up to the next order of magnitude and say x is now 10. Now if I go 10 cubed, that's 1 with 3 zeros. And then 10 squared is 1 with 2 zeros, so we'll multiply that by 2. And then 10 times 1 is just, 10 times 3 is 30, and then plus 4. So if I put that all together, 1,234. Up to the next order of magnitude, x is 100. So 100 cubed is 1 with 6 zeros behind it. It's a million. Then 100 squared is 1 with 4 zeros, so this times 2 is 2 with 4 zeros. And then 3 times 100, then 4. So we're looking at 1,020,304. Put the commas. It's a little over a million. Let's go up to the next order of magnitude. X is now 1,000. So 1,000 cubed is 1 with 9 zeros. That's not enough zeros, sorry. Then 1,000 squared is 1 with 6 zeros. Multiply that by 2, and I get 2 with 6 zeros. Then I go to 1,000 times 3, and then I add 4 at the end. So with all this combined, I can say this is this with the commas. Now the pattern I want us to notice is that when x is just 1, 1 cubed, 1 squared, and 1, those are all just 1. So the contributions of each of these terms are on the same order of magnitude. But when x goes up to 10, what we notice is that the leading term contribution starts to pull away from everything else. Because 10 cubed is, by definition, 10 times as big as 10 squared. And then we go up to 100, and 100 cubed is 100 times as big as 100 squared. And 1,000 cubed is 1,000 times as big as 1,000 squared. So we notice that the leading term becomes bigger and bigger and bigger compared to everything else. So if we look at the final number, we might even say, at this stage, we could easily round this to 1 billion, and it wouldn't even make a difference, would it? Those numbers are so small compared to this 1 billion that we can start saying, as x gets bigger and bigger and bigger, the behavior of the function is determined by the leading term. None of the rest of that really has much of an effect on what f of x does. As promised, let's talk about end behavior. So our function, we had f of x is equal to x cubed plus 2x squared plus 3x plus 4. And what we want to consider in the graph we want to consider as x goes very far to the right. And the way we express this, I'm going to put down end behavior, we want to express this as x goes to infinity. Now what this means, because infinity isn't a number, infinity is an idea. It says as x gets bigger and bigger and bigger and bigger, we write that as x approaches infinity. In the graph, what that means is as x goes very, very far to the right. So what happens is, as x becomes a very big number, we've already declared that these terms don't really affect the behavior of f of x anymore. We are dominated by x cubed. So a very big number times itself is an even bigger number. But the most important thing is it's a positive big number. So we say as x approaches a very big number, f of x also goes to a very big positive number. Now what that means is, as our graph goes toward the right, our graph also goes up, because the result of a positive big numbers cubed is a positive big number. So we're going to say our graph goes that way. Now the other type of end behavior we want to consider is as x approaches negative infinity. So this, once again, infinity is not a number. This represents the idea that x is becoming very, very, very negative. So I suppose you could call that a very small number, but that sort of raises some conceptual confusion. So I'm going to call this a very negative number. So like think negative a million, negative a billion, negative 1 trillion. That means I'm going very far to the left in the graph. So if I take a negative number and I cube it, I get negative times negative times negative is negative. But it's a very negative number. So f of x approaches negative infinity. So what that means is that as my graph goes very far to the left, my graph goes very far down. And in between, we might have some interesting behavior, but that's not what we're worried about right now. We are worried about the end behavior. So as x goes to positive infinity, this means y goes to positive infinity. As x goes to negative infinity, a negative number cubed is negative, so y goes to negative infinity. And those two put together are the end behavior of this function. Let's try another example. So let's say our function, f of x, is negative 5x to the fourth plus 2x cubed plus 25x minus 3. And we want to know the end behavior of this function. So this is going to be as x approaches infinity. What that means to us is as x becomes a very big positive number. So as we go to the far right in our graph, what will happen? Well, we've already decided that as x becomes a very big number, that the contributions of all the powers except the biggest power don't matter as much. So really, I'm only looking right here and I'm ignoring the rest. So as x becomes a very big positive number, a positive number to the fourth is still a positive number, a very, very big positive number. But then I take that and multiply by -5, and I get a very negative number. So as x goes to the far right, I get a very negative value for y. So f of x approaches negative infinity. Then if we consider the other end, as x approaches negative infinity, so I become a very negative number, I'm going to the very far left, a very negative number to the fourth power. Well, negative times negative times negative times negative, an even number of negatives is positive. So at this stage, x to the fourth is a positive number. Then I multiply by -5 and I get a negative number. So once again, I have negative infinity. So we've noticed two things that happen, right? One is if the number in front of the leading term, so that's the leading coefficient right there, that -5, if that number is positive or negative, it affects our analysis. We've also noticed that depending on the actual power there, so that's the degree, right, the biggest power on x. If that's odd, then we have alternating behavior, and if that's even, we have the same behavior to the right and to the left. We're going to generalize this in a moment. Now let's summarize what we learned in the last two examples in what we call the leading coefficient test. And I'm going to put in parentheses end behavior because the leading coefficient test really tells us about the end behavior. In the most general sense, I can write a polynomial function in the following way. I can write it as a sub n times x to the n. And remember, this means x to the n power, that's just the biggest power I get. And then a sub n means it's the coefficient on that term. So I can write the next term as a sub n minus 1 times x to the n minus 1. That just means it's one power less, and then that's the corresponding coefficient. And we keep writing them. A sub n minus 2, x to the n minus 2, plus dot dot dot, and I keep going up to a sub 1, x to the 1 power, and a sub 0. And then we remember that in the end behavior, the term that dominates the behavior is that, and none of the rest of them really matter, because the contribution of the next highest power is small compared to this, so small that it barely affects it. So this n, remember, is the degree. That's the biggest power on x. The degree is n. And this number out front is what we call the leading coefficient. And as the name implies, the leading coefficient test is going to tell us stuff based on this number right here. So there are 4 cases that we're going to consider. So case number 1, we're going to say the degree is odd. And the leading coefficient is positive, so it's bigger than 0. So let's say as x approaches infinity, that means x is going to become a very big positive number. So we go far to the right. So when you have a very big positive number to an odd power, well, a positive number to any power is going to stay positive. So the big positive number times a positive leading coefficient is a positive number, and it's very big. So I'm going to end up going in that direction. Then, as x approaches negative infinity, so I'm going toward the left, a negative number to an odd power, that's an odd number of negative signs, is going to be negative. So a negative number times a positive number is negative, and it's very, very negative. So I'm going to be going down this direction. And in between, I can have all kinds of behavior depending on the other terms. But the biggest power is what governs what happens on the ends. Case number 2, n is odd. But what changes is that the leading coefficient this time is negative. So as we go toward the right, as x approaches infinity. So I have a positive number to an odd power. That's still positive, very big positive number. But then I'm going to multiply by a negative number. So as a result, I'm going to get a very negative number. So as x goes to the right, y becomes very negative. I'm going to go down in that direction. Then as x goes to negative infinity, so a negative number to an odd power is negative, multiplied by a negative leading coefficient. So negative times negative is positive, a very big positive number. So in this way, as x goes toward the left, y is going to go up. Notice for the odd degree polynomials, we're going to have alternating end behaviors. Let's see for the even ones. So case 3, n is even. And we're going to let the leading coefficient go back to positive. So let's say, as x approaches infinity, okay, so we're going to have a very big number, positive, to an even power, definitely positive, multiplied by a positive leading coefficient, still positive. F of x is going to go to positive infinity. So that means as I go toward the right, I'm going to rise. Then let's say as x approaches negative infinity. So a negative number to an even power is positive now. So positive times a positive leading coefficient is positive. So our y value is very positive. That means as x goes to the left, y goes up. Oh, it's different this time. The end behaviors are not alternating in the case when I have an even degree. Let's finish it out with the last case. N is even, but the leading coefficient is negative. Okay? So in the graph, we have as x approaches infinity. So we're going to say a positive number to an even power. That's positive. But this time our leading coefficient is negative, so we're taking a positive number multiplied by a negative number, which gets us a very negative number. So f of x is going to approach negative infinity. As x goes to the right, y goes down. Then, as x approaches negative infinity, so I have a negative number to an even power, which we know is positive. So we have a positive number here multiplied by a negative leading coefficient. Negative times positive is negative. So f of x goes to a very negative number. That means over here goes down. So once again, even degree, we have non-alternating end behaviors. So if you can look at these and not just remember them, but understand why they happen, you will be able to look at any polynomial function, identify the degree and the leading coefficient, and then decide what the end behavior should be on that alone. Let's do some quick examples to lock in that idea. So we'll say example 1. The problem statement is going to be state the end behavior of each function. Part A. We'll say f of x equals negative 5x to the 6th plus 2x cubed minus 8. Now, for end behavior, we're really only interested in the biggest power of x. So that's 6 right there, that's the degree. Degree is the highest power of x. Then we look at the coefficient attached to that x to the 6th. That's going to be the leading coefficient. So if we apply the leading coefficient test, and we think about the graph, we're going to say the degree is even, which means we're going to have matching end behaviors, either that way or that way. And the leading coefficient is negative 5, which means as x goes to a very big number, a big number to the 6th power is going to be positive, multiplied by a negative is going to give me very negative. And I'm going to have matching end behavior. So I would say, as x approaches infinity, that means I go toward the right, my y is going to become very negative. As x approaches negative infinity, going toward the left, my y is going to become very negative. And there we have it. This is a statement of the end behavior. Let's do part B. Let's say g of x is equal 15x cubed plus 9x to the 4th plus 2x to the 13th power. But don't be fooled. The highest power of x doesn't have to be written in front. It's still the highest power of x. So in this case, the degree is 13, the highest power of x, which means the leading coefficient is going to be the coefficient on the x to the 13, so that's the 2. So now let's think about the graph. And the degree is odd, which means we're going to have alternating end behavior. So let's think about as x approaches positive infinity. Well, that means this number, very positive, going to an odd power, still very positive, multiplied by a positive number in front, which means the y value is going to go very positive. So as I go toward the right, my graph is going to rise like that. Then as x approaches negative infinity, a negative number to the odd power is a negative number, times positive is going to give me a negative overall. G of x is very negative. So if I go toward the left, I'm going to go to a very negative number. And as we suggested, we're going to have alternating end behavior. This, put together, is a statement of the end behavior. Sound good? The last thing I want to talk about in this video is how to transform basic polynomial functions. So let's start with an example, f of x equals x cubed. Now, we know that the end behavior is going to be alternating because it's an odd degree, and the leading coefficient 1 is positive, so we know we're going to be up over there and down over here. So if I carefully fill out the parts in between, I'm going to end up with something like this. And next, I want to graph the following. So I recognize this structure right here. This is a cubic. So I can rewrite g of x in this form. Because f of x plus 1 means take this x plus 1, plug it in, and cube it. So this x plus 1 cubed is the same thing as f of x plus 1. And hopefully in this format, it's obvious that g of x is a transformation of this function, where I take a vertical dilation of 2. So I'm going to say vertical dilation, where I take all the y values and multiply by 2, and then I shift to the left one, because it's a plus 1 here. So I'm going to shift to the left by 1, and then I'm going to shift up by 5. So if I take this graph and then modify it, I should take my origin and move it to the left 1 and up 5. So it's going to be up 1, or sorry, negative 1 comma 5 is right here. And then I'm going to take the y values, stretch them by 2, and shift them into place. So I'm going to be twice as tall. And this section should be a little bit flat in here. Great. So that's one example. Let's try another one. So let's say h of x, another example function, is x to the 4th power. So this time the degree is even, so we're going to have matching end behavior. And the leading coefficient is positive, so we're going to have up over here and up over here. Now what's going to happen is we're going to have a very flat midsection and incredibly steep. Flat midsection and incredibly steep. And this should be symmetric on both sides. Now, I would like to graph j of x equals negative 1/2 x minus 2, and I'm going to put to the 4th power plus 1. So I recognize that 4th power structure is a transformation of h of x. I can understand this as h of x minus 2 plus 1. This is the same as that, because if I take x minus 2 and plug it in here, I get exactly that. So I should recognize there's a vertical dilation factor of -1/2. So I can write this as a vertical dilation where I take my y coordinates and I multiply by -1/2. And multiplying by a negative means I'm going to end up reflecting over the x-axis in the process. I'm going to be shifting toward the right 2 and up 1. So I'm going to say shift toward the right by 2 and then shift up by 1. Now let's produce a graph. So I'm going to take this, flip it upside down, and multiply the y coordinates by 1/2. So I'm going to shrink it. Then I'm going to shift to the right 2 and up 1. So right 2 and up 1. 2, 1. And then this is going to be flat midsection, but then incredibly steep. Flat midsection, and then incredibly steep. And I'm going to have a graph that looks something like that. All right, now hopefully this discussion on end behavior wasn't too confusing, because we did involve this idea that x is becoming a very large number or a very, very negative number without specifying exactly what x is. That's sort of how end behavior works. But if you can remember shapes, so if you think about degrees being odd or even, having alternating end behaviors or matching end behaviors. And if you can look at the leading coefficient and argue that if the leading coefficient is positive or negative, certain things happen at the end of the graphs. In the future, we'll be able to discuss what happens in the middle parts of the graph, and we'll talk a lot about intercepts and roots and factors and all these things. Thanks for tuning in. Take care.